welcome. This video will be about the fundamentals of probability, wherein I will be talking about its very basic concepts. Now, this will be intended for those who are quite new to the concept of probability and to biostatistics for that matter. Now, majority of the concepts I'll be tackling will be making use of data coming from this 2011 New England Journal of Medicine article. The authors concluded that the test drug eplerenone, which is an aldosterone-specific mineralocorticoid receptor blocker, reduced both the risk of death and the risk of hospitalization among patients with systolic heart failure and mild symptoms. Now, this conclusion was based on this study, which involved 2,737 patients from 278 centers in 29 countries. Now, these patients had NYHA class 2 heart failure and an ejection fraction of 35% and less, and they were followed up for a median period of 21 months. Now, studying all patients with class 2 heart failure and ejection fraction of less than or equal to 35% in the whole world is of course not possible. So the investigators had to make inferences to a larger population of patients based on the sample they studied. Now, in real life, one cannot be sure that a particular patient with such designations will respond to treatment as the average patient did in this study. But one can use the data to find the probability of a positive response. This leads us now to the question, what is probability? Now, probability is defined as the extent to which an event is likely to occur. Now, the concept of probability is not new or alien to physicians such as myself, or to health workers for that matter. Actually, probability is frequently included in everyday communication between health workers and in communication between health workers and their patients, or the patient's relatives for that matter. As these examples suggest, most people express probabilities in terms of fractions. If we divide the numerator by the denominator, we get a number between 0 and 1. And from here, we could actually derive percentages by multiplying them by 100%. The more likely an event, the closer the number is to 1. The more unlikely the event is, the closer the number is to 0. Similarly, an event that cannot occur has a probability of 0, and an event that is certain to occur has a probability of 1. Now, before we move on, let's first define a few terms. The first term is experiment. Now, this is defined as any planned process of collecting data. In the case of the journal article we will be using, the experiment is the process of determining the risk of death and the risk of hospitalization among patients with systolic heart failure and mild symptoms. The next term is event. It is an outcome or a set of outcomes to which a probability is assigned. Now, an event defines what is called a complementary event, which is the event opposite of the event of interest, something that I will talk about later. And together, these define what is called a Bernoulli trial, which we will look into as well later. Now, let us assume that an experiment can be repeated many times. Each repetition or replication is called a trial. Now, assuming that one or more outcomes can result from each trial, the probability of a given outcome can be determined by dividing the number of times that outcome has occurred by the total number of trials. Finally, we have the term universe. In the statistical sense, it is defined as the representation of the entire group of units which is the focus of the study. In our case here, the universe will be all of the 2,737 patients included in the eplerenone study. Now, contemporary statistics now regards probability as either objective or subjective. Objective probability can be further categorized into classical and relative frequency probability. Let's first start with classical probability. Now, assuming that an event can occur in capital N number of mutually exclusive and equally likely ways, and M number of these events possess a trait, which we will designate as capital E, the probability of capital E occurring is equal to M divided by capital N. Daniel and Cross in their textbook gives the example of a deck of playing cards. Capital N here will be 52, which represents the total number of cards in a deck. Let us say that the trait, capital E, that we are interested in is the Jack. So, if a card is picked randomly from a well-shuffled deck, the probability of picking a Jack is 4 over 52, or 7.7%. Similarly, if the trait of interest is the suit of spades, the probability of picking a spade is 13 over 52 or 25%. Now take note that each card has an equal probability of getting picked or selected. Now this type of probability is also called the a priori probability, because this probability is computed by logically examining already existing information. In the case of deck of cards, we already know beforehand that there are 52 playing cards all in all, there are 4 jacks, each representing each suit, and there are 13 cards with the suit of spades. By using this information, we were quickly able to determine the probability. The other type of probability which researchers tend to be more accustomed with is the relative frequency probability. Unlike classical probability, the relative frequency of an event occurring is known only after an experiment is done. Thus, this type of probability is also called a posteriori probability. For that matter, this approach to probability depends on the repeatability of an experiment and the ability to count the number of repetitions, as well as the number of times that some event of interest occurs. As you can recall from earlier, in the eplerenone study, the experiment involves randomizing each patient with systolic heart failure and mild symptoms to receive either the drug eplerenone or a placebo, on top of the heart failure treatment they are already receiving. The risk of death and the risk of hospitalization among these patients are then determined during the follow-up period. Now take note that the formula that we use to determine the probability of trait E occurring is basically the same as that of classical probability, except that we use lowercase n instead of uppercase N. Now this is because we are only dealing with a sample of a much larger population. Thus, the ratio m over n is only an estimate of the probability of trait E occurring, which we infer on the population of class 2 heart failure patients at large, since it is impossible to test every single heart failure patient in the world, let alone repeat the experiment more than once. Now, because of financial and logistic reasons, amongst other reasons, the study was only done once with a large group of patients, that number being 2,737. Now, given that limitation, we often view each patient enrolled in a study as one repetition of that experiment, which we follow until a particular event of interest occurs. Now, a sample size of 2,737 should be large enough to make reasonable probability estimates. Now, with regards to subjective probability, I will only be mentioning this in passing since the particulars about this type of probability are beyond the scope of this video. In contrast to the relative frequency approach to probability, which relies on the use of experiments and their repeatability, subjective probability is demonstrated more by someone's hunch, personal belief, or gut feeling about whether an event or outcome will occur. An example of a method that makes use of subjective probability is the Bayesian method, named in honor of the English Presbyterian minister and statistician Thomas Bayes. This method makes use of prior and posterior probabilities, the definitions of which are flashed on our screens. Though this type of approach to probability has gained an increased amount of attention as of late, it hasn't been fully accepted, particularly by frequentist statisticians. In medicine, however, subjective probabilities are important in their own right because they form the basis of a doctor's opinion about whether a patient has a specific disease or not. An introduction into Bayesian methods would be a great topic for another video, however, it is beyond the scope of this video. If you have interest in such methods, it is best to be referred to the appropriate textbooks and materials that discuss such methods. Now, let us get into the article about the eplerenone study. Let's look at Table 3, which features the adverse events experienced by patients while being treated in their respective treatment arms. Note that information about adverse events was available in 1,360 of the 1,364 patients in the eplerenone group and 1,369 of the 1,373 patients in the placebo group. Now let's focus our attention on this part of the table. So this table here is an excerpt of Table 3 of the article. For ease of discussing the computation of different probabilities, I included both row and column totals. For purposes of exercise, I've added another category, no adverse events, to represent the proportion of patients in each arm who did not experience any adverse events. I derived the frequencies by subtracting the subtotal of the frequencies of adverse events from the total number of patients randomized to each treatment arm. Now that we have this table, suppose we pick a patient at random from this sample of 2,729 patients. What is the probability that this patient will be in the eplerenone group? For purposes of illustrating the calculation of probabilities, we consider this group of 2,729 patients to be the largest group for which we have an interest. We also assume the two groups, namely the eplerenone group and the placebo group, to be mutually exclusive. We assume as well that the likelihood of selecting a patient is equal to the likelihood of selecting any other patient in this large group. Our characteristic of interest is being a member of the eplerenone group. In order to derive the probability that a randomly selected patient will be in the eplerenone group, we take the total number of patients randomized to the eplerenone arm and divide it by the total number of subjects in this study. Now our desired probability then is 0.4984. We call this type of probability marginal probability. The term marginal is used because the numerator of the probability appears in the margins of the contingency table. In this case, the numerator is a column total 1,360 representing the eplerenone group. With marginal probabilities as well, the total of the whole group, which in our case was 2,729, is used as a denominator. Now, this type of probability is also known as unconditional probability because no conditions were imposed to restrict the size of the denominator. In our case, we wanted to know the probability of a patient coming from the eplerenone group, ignoring whether or not any other event has also occurred. Now, it's possible that this concept may seem a bit difficult to visualize at this point, but I think the succeeding examples would hopefully make things clearer.